In the meantime, we're going to move on to the next type of distribution. So we've looked at, just remind me, what distributions have we looked at so far? Uniform distribution. Now, what's a uniform distribution? Can anybody remember? Good, so the probability of each outcome should be the same. It's uniform, right? What was the distribution we looked at yesterday? Binomial. Now, what's a binomial distribution? Two outcomes, and specifically, what are those two outcomes? They've got to be discrete, yeah, good, but it's got to be a success or a failure, yeah? So if it's a success or a failure, also if you do something for a fixed number of trials, and all of those trials are independent of each other, then it's a binomial distribution. So there's three things you need to satisfy. Fixed number of trials, all of those trials are independent of each other, and it's got to be discrete, okay? And as guess as well, success or failure, okay? So if all those things are satisfied, then you know it's going to be binomial. Now we're going to look at a new distribution now, which looks at things from a slightly different perspective. So it's related to binomial, and you'll see that a bit later on. But for the moment, can you all stand up for me? Okay. So what we're going to do is we are going to take our heartbeat. Okay, so we're going to take our pulse. So if you don't know how to find your pulse, there's two places you can calculate, well, three if you count your pedal one as well. The easiest one I think is going to be on the wrist. Okay, so you should be able to feel a vein on the inside of your wrist. Use two fingers. If you can't find it, use your neck. Okay, there's an artery in your neck as well which you can use. Now you should be able to feel it pulse. Has everybody got themselves a pulse? I hope so, because otherwise I don't know why you're still here. Okay, good. So what I'm going to do is I'm going to time for 10 seconds. And all I want you to do is count the number of pulses that you get in that 10-second period. Is that okay? Right. So when you're ready, then we'll make a start. So 3, 2, 1, start counting. Right? Now you should have a number. Can you write that number down for me? So once you've done that, we're going to do it again. So we're going to do this 5 times because I want to increase the quality of the data which we collect. I'm going to do it more times. So can you get ready to find your pulse again? And we'll do exactly the same thing again. You ready? Okay. 3, 2, 1, start counting. Stop. Okay, so again, you have another number. Copy that number down for me. And you'll get ready to do it again. Okay. Okay, so ready? 3 more times. 3, 2, 1, start counting. Stop. So again, write that number down for me. Okay, 2 more times. Ready? 3, 2, 1, start counting. Stop. So again, write that number down and we'll do it once more. So you're ready last time? Okay, 3, 2, 1, start counting. And stop. So again, write that number down. Okay, thank you very much. You can all sit down now. Now here's what I want you to do. With those 5 numbers, I want you to find the average. Okay, I want you to find the average. Now again, it's up to you which average you want to use. I would suggest maybe using the mean here because you don't necessarily expect outliers. Okay, so just give me the average. Okay, find me the average of those 5 numbers. Have you all got a number? Good, fantastic. Okay, so here's what I'm going to do. I could go around the class and ask for all of your numbers, okay, and then take the average of those, right? But in fact, just because I've got you each to do it 5 times, I'm just going to select somebody at random. So Nikki, what is your heart rate? What's your average heart rate? 13, okay. So in other words, how I could write this is the expected number of heartbeats. You notice how I've defined my random variable. It's the number of heartbeats in a 10-second period. The expected heart rate is going to be 13, yeah? And hopefully you've all got a number somewhere around 10 to 15. Am I right? Yeah? So what I literally got you to do there is to look at a rate, okay? So that's a really important word, a rate. What does the word rate mean?
Speed.
Not quite speed.
Frequency?
Not quite frequency. What does the word rate mean? What does it remind you of? Sorry, what? Yeah, physics. So what in physics specifically? Okay, fine, fair enough. I mean, we'll meet this idea of rate again when we look at mathematics, okay? So we'll look at the rate of change, okay? I understand why you said speed, okay? I understand why you said speed. I think actually rate is better related to time, okay? So rate is something to do with time. Specifically in this case, it's the number of heartbeats that you're getting within a given period. So you're literally finding your heart rate, yeah? It's how quickly or the time it takes for you to beat in those 10-second periods. Is that okay? Yeah? So when there's a rate happening, so something happening with relation to time, how quickly something is happening, then it's more likely that you're going to follow something called a Poisson distribution, okay? So in this case, you notice how we set it up. Okay? So if there's a random variable that you think is more related to time, then think it should be related to Poisson distribution. So in this case, what I literally said is count for 10 seconds. That's your time period. How many heart rates do you get in 10 seconds? What's the expected number of heart rates in a 10-second period? Okay, and Nikki's heart rate was 13. Does that make sense? Okay, so if you have a situation that is related to rate, in other words, time, how quickly something is happening, then it should be following something called a Poisson distribution. Okay? Now, what if I wanted to do it again? What if I wanted to do it not for a 10-second period, but change the period to maybe 20 seconds? Okay, so let's define another random variable. Let's say y is the number of heartbeats in a 20-second period this time. Well, I mean, I could get you all to stand up and do it again, but this time count for 20 seconds instead of 10 seconds. But do I need to? Do I need to do this again? Do I need to do this experiment again? Given that I've already done this, can I find out what this is going to be?
Roughly, yeah.
Yeah, roughly. Why?
Because it's continuously, my heart is...
Okay, I wouldn't say continuously, I would say constant instead. Yeah? So in other words, something is happening, not just any rate, but at a constant rate. Okay? So if something happens at a constant rate, I mean your heartbeat is relatively constant in the way that it beats, except if you do exercise and things like that. But we can assume we're all resting, right? We've all calmed down and given you 5-10 minutes to relax. Okay? Something is happening at a constant rate, you have to define the time period that you're looking at. Okay? So you notice how I define my first random variable. It's the number of heartbeats in a 10-second period. So I've defined the time which I'm looking at. Okay? But it now means that I can change it to another random variable really easily. Because I know that something happens at a constant rate, my heartbeat happens at a constant rate, then if I wanted to change it, so instead of looking at a 10-second period, I look at a 20-second period, I could really easily do that. Does that make sense? So what would the expectation of y be? Given the expectation of x is 13. Yeah, it's just that times 2, right? Which is 26, right? If I wanted to change it again, not to a 20-second period, but a 30-second period. So let's say z is the number of heartbeats in a 30-second period. So now it's 30 seconds. What would the expectation of z be? 39. Fantastic. Okay. So can you see that because I have a situation that is working at a constant rate, something is happening given a time period at the same rate. It's happening at the same kind of speed, the same time. Okay. Then it's just really easily to work out what the other random variables are. But you notice that x is a different random variable to y, which is a different random variable to z. Do you notice that? Because you notice in my definition of the random variable, when I define my random variable, I have to define the time period that I'm looking at. So is it 10-second period? Is it 20 seconds? Is it 30 seconds? As soon as I change that time period that I'm looking at, it becomes a different random variable. Does that make sense? Okay. So let's have a think then. Let's have a think. What do you think the parameters of a Poisson distribution is going to be? What do you reckon? So what's the only data which we needed in order to do our heartbeat? What's the only thing that we needed to collect? So what's the only piece of information that we needed in order to work out the expectation of x? What's the only thing that we collected when we did that experiment? The rate. Does that make sense? The only thing we needed was the rate. In this case, the rate was 13 for a 10-second period. The rate for a 20-second period was 26 heartbeats. The rate for a 30-second period was 39 heartbeats. Does that make sense? So the only piece of information, the only parameter that we need is the rate. Okay? So let me formalize this for you. Okay? Let's deal with this one. So x. I know that because something happens at a constant rate, my heart rate happens at a constant rate, then it's going to follow a Poisson distribution, which we write like this. So x is distributed using a Poisson distribution. So I don't just write p. Why don't you think I just write p? Yeah, it gets confused with probability. So I have to write PO for Poisson. Okay. By the way, if you speak any French, Poisson means fish, right? It's not a fish. It's named after a mathematician called Poisson. Okay. So x is distributed Poisson, and then the only parameter that I need is my rate. Okay. So I give the symbol lambda to represent my rate. So in this case, I would say that x is distributed using a Poisson distribution, and my rate I worked out was 13 beats per 10 seconds. Yeah? If I wanted to define this one, y would be distributed using a Poisson distribution with a rate of 20-second beats in a 20-second period. Is that okay? If I wanted to do z as well, just for completeness, I would say z is distributed using a Poisson distribution with a rate of 39 beats in a 30-second period. So you notice now that I have to define the time period that I'm looking at, okay, in order to define the rate. Because otherwise, this rate is going to change depending on how long I look at it. Is that okay? Yeah? Okay.